Hello, everybody. Welcome back. First in-person cow for quite a while. So thank you to those who come in person. Thanks to those who come online. Our first talk is going to be by Gregory Sankaran, and he is going to tell us about, I have to type on my phone, Kodaira dimension of Kuga varieties. I think Kuga varieties in there somewhere. Yeah, thank you very much.
Okay, I think I'm allowed to take my mask off while I lecture.
Oh, also, are you okay to be recorded?
I'm okay to be recorded. So thank you for the invitation. I wasn't the advertised speaker. The advertised speaker went to France and has been, therefore, is now having to isolate. So I'm going to talk about the Kodaira dimension of Kuga varieties. In some sense, this is an old story. I mean, there's nothing, there's almost nothing here that couldn't have been done quite a long time ago. But there are reasons why it's come up now. Also, if it's an old story, maybe it's not so familiar to some people who weren't around in the old days when this was a new story. So maybe that's not such a bad thing either. So ultimately, this is about moduli of abelian varieties. So I'm writing on a blackboard for the first time for several months, so that's another unfamiliar thing. So what I'm describing is joint work with Riccardo Salvati Magni, no hyphen, in Rome, and my research student, Flora or Winke Poon, who is in the room somewhere. And I have actually given a version of this talk already in virtual Kobe sometime in February, which had only Riccardo's name on it. And so there have been some changes since then, and Flora's got involved. And I might say where, but I mean, it's joint work. Okay, so Kuga variety is by this I mean something of sort of obviously illegal, which is the universal families over moduli spaces of abelian varieties. And for the purposes of this talk, that's going to be with the principal polarization and nothing else. And of course, this is highly illegal because abelian varieties with principal polarization have automorphisms, -1, and some of them have more than that. And so there isn't a nice universal family unless you talk about families over the moduli stack, but that's not what I mean. So this is an abuse of the word universal, because I can, nevertheless, there is a construction, and it's not sort of difficult to write down very explicitly, that so it's not really a universal family, it's a tautological family, if you like. So the fiber is, well, because of the -1, it's actually going to be the Kummer variety. By the fiber, the general fiber. I mean, there's a fairly recently some lecture notes of Kuga that have been fairly recently published or republished, dated originally from the 1960s. And Kuga does this not for principal polarization, but for some level structure that kills the kills the automorphisms, but actually you don't really have to do that. There's just for the purposes that he was interested in, that was a sensible thing to do. But there is also some interest in doing this. I mean, for example, for non-principal polarization or whatever. I'm just going to make the assumption, I might possibly say a bit about some other cases, but I'm going to be interested in g greater than or equal to 3. G equals 2 is a bit different, I might conceivably say a little bit about that at the end, but basically I'm interested in g greater than or equal to 3. So this is not a new thing at all. It's been looked at by quite a few people, but okay, so there are two generalizations of this that you could write down. So the first one I'm actually going to use, which is that I'm going to consider the n-fold Kuga variety X NG. So the fibers here are n-fold product, just the Cartesian products as n-pointed, n-ordered points, I suppose, on the Kummer variety. Okay. And then n is greater than or equal to 1. And the other thing you could do is you could look at so the moduli space of abelian, principally polarized abelian varieties is associated with the symplectic group SP2GZ. It's a quotient of the, I'm working over the complex numbers all the time, and working over the complex numbers, that moduli space, that coarse moduli space is Siegel upper half space divided out by an action of SP2GZ, but I could replace that SP2GZ by some arithmetic subgroup. So impose some level structures, non-principal polarizations, whatever else. Replace SP2GZ by some other gamma. If gamma doesn't contain -1, then I don't have the Kummers here, I actually have the abelian varieties themselves. So there are various generalizations that one could look at. Some of them are interesting, some of them are less interesting. But I'm really interested in these ones, this AGN. Okay. Okay, so let me start by actually stating what the result is. So I should say that this is still work in progress to some extent. I mean, we've got all the bits, but they're in scraps of paper on my desk and odd emails from Flora and bits of, just is a mess at the moment. I'm tidying it up. So this is work in progress, and I don't absolutely promise that everything I'm writing is absolutely correct, but I'm fairly, I wouldn't be standing here if I wasn't pretty sure. Theorem. Suppose g greater than or equal to 3 and n greater than or equal to 1. So I'm not just looking at AG. Then the Kodaira dimension kappa xgn. And by that, I mean the Kodaira dimension. So this is a quasi-projective variety. And so I say, so by Kodaira dimension, I mean, I take some compactification and I resolve the singularities. And then I've got a projective variety, and I can talk about the Kodaira dimension of that. I don't mean the log Kodaira dimension or anything like that. This is a birational invariant. The Kodaira dimension, and I can actually tell you what it is, I believe, in all cases. It is half g plus 1, that's to say the dimension of AG, which is the most it can be because the fibers have, being Kummer varieties, they have Kodaira dimension 0. And in this case, Itaka's conjecture is known. So this is the most that the Kodaira dimension can be. And it is that. So this is kind of relatively general type, if you like. And this is, and then I'll say it this way, if G plus N is greater than or equal to 7, it's minus infinity in all other cases, except that the Kodaira dimension of, and at this point I better put my glasses on so that I actually read this correctly. Kappa of x5, 3, and kappa of x3, 4, this is n and g, those are both 0. And the other one is that kappa of x4, 3 is actually minus infinity. So that's the this. Sorry, yes, is. Is that better? So can actually tell you the answer in all cases. I mean, just to remind people, tell people who don't know this, the Kodaira dimension of AG itself is known for all G except G equals 6. And for a very long time, G equals 6 is a complete mystery. And we now know, we've known for a couple of years now, that AG, the kappa of AG is not minus infinity. That's all we know. So that's the one remaining mysterious case. So this tells us that these ones are sort of better behaved. It's really only 6, 0 that's still mysterious. Okay, so I mean, this is going to be very similar to the way that one deals with Kodaira dimension of abelian moduli of abelian varieties. We're going to write down suitable modular forms. Fortunately, people have already done that for us. Mostly Mumford already did that for us, or line bundles whose sections will be modular forms. You don't necessarily write them that way. And then we're going to worry about singularities. But it's not quite as straightforward as that. Okay, now, okay, so I'm going to experiment with the boards and see what happens if I do that. Well, that looks okay. And I think that should be good. I've walked into the picture. Okay, so the board I'm about to write on should be the one on the screen. Good. Okay, so the most recent thing that I'm actually going to use is that a couple of years ago, Shohei Ma in Tokyo looked at these things and showed that there's an isomorphism of graded rings between the pluricanonical ring of AGN of XGN and a certain space of modular forms. So I just have to get the numbers right. So this is the direct sum over M of the modular forms of weight, and it's G plus N plus 1 M for the appropriate group, which in this case SP2GZ. Okay. Actually, this holds much more generally. I mean, this holds for any finite index subgroup of SP2GZ, and there's an old paper of Hatada from about 1983, which proves this, presumably for different reasons, if you replace this SP2GZ by torsion-free gamma, then it's been known for some time, but this is still all right. So that's the first thing, and then then Ma also proves the following statement about what happens at the boundary. So this is still Ma. So suppose there is a compactification X bar of so xn of gamma is the, so this, again, this is gamma is so I'm writing a slightly more general statement than I'll use because I'm always going to be looking at the full SP2GN, but 2GZ, but this doesn't depend on which subgroup it is. And the compactification is should satisfy certain conditions. So the first thing is it should be normal. It should be toroidal, by which I mean that, so you have a map from XNG of gamma to AG gamma. Okay, so I mean, forget this gamma really. I mean, if you give me, so this is Zeekel upper half plane modulo gamma. But forget this gamma really. It's just think of it as being SP2GN, 2GZ. So this map should extend to a map which I'll also call F, that goes from X bar to some toroidal compactification of AG. So it sits over a toroidal compactification. And then the third thing is that this shouldn't be contracting divisors. So Well, when I say contracted, I'll say what I mean in a moment. So what I mean is that if you give me an irreducible component of the boundary of this one, then it should surject onto an irreducible component of the boundary of this. So I don't really mean it's not being contracted. I mean that the codimension remains what you would expect. So the fiber dimension doesn't jump, I suppose is what I mean. So every irreducible component of, let's call it delta x, boundary here, dominates an irreducible component of delta A. I've dropped the gammas now. Okay. Okay, and if that happens, if all those things happen, then the conclusion is that, again, we have an isomorphism of graded rings, and now we've got x bar and nth tensor power of k bar, and then we want m delta x here, so things with that vanishing, and then those should be the direct sum over m greater than or equal to 0, and then m g plus n plus 1 m of gamma, and that's the only real reason I need the notation gamma. Okay. And so Ma uses this to get some results about Kodaira dimensions, because in some cases he can actually get at PG. He can actually see some non-vanishing for some of these spaces, and therefore for some of these plurigenera. Because these aren't really plurigenera because of the mx of the m here. But for example, if m equals 1, then you can't have exactly that. So there are various things. So in fact, what you do, so actually what you can do is, if you know that there are cusp forms in here, then they vanish. So this thing, this doesn't affect anything, and you just get a section of, so the m equals 1, you just get a section of k. And so if he knows when there are cusp forms of the appropriate weight, then you get some, you get actually PG positive, and therefore Kodaira dimension can't be minus infinity. Okay, so that's fine, yeah, he does more than that in his paper, but the but we can do something else. So what these are doing is they're linking together K and delta, and then implicitly here what they're doing is telling us how that compares with the Hodgkin bundle. And so in principle, what this does is it reduces the study of this Kodaira dimension to understanding the slope of modular forms. So yeah, there you've got L, the Hodgkin bundle here, and then you've got order of vanishing at infinity here. And so this weight and this order of vanishing, that's telling you about the slope of the cusp forms. And this is something that's well studied by people who've thought about Siegel modular forms. So there's plenty of information. Okay. So what I'm going to do is to assume for a moment that compactifications like this with satisfying these conditions actually exist. But that's non-trivial. It's not at all clear that that's actually really the case. So in the draft paper that we have, I call these Namikawa compactifications. And the reason I do that is that the first attempts to write down things a bit like this, to write down compactifications satisfying at inner condition 2. Some of these are written down by Namikawa in the 1970s. I'll say a little bit more if I don't run out of time, which I probably will, about what he actually did. Okay, I'm going to see if I can get that board to work. Those ones are smaller. Maybe that means I need to be more careful with the. Maybe if I keep doing that, it will just go all the way around. I don't know. I can also go up and down. It'd be very confusing if that went all the way around. Oh, it's okay. Let's try this. Okay, so let me just remind you of a few bits and pieces. Recall that. That's to say, pretend that you remember having been told this before. And I'm going to take G, I allow G equals 2 for a moment, but not G equals 1. So a modular form of weight K is a holomorphic function phi from the Siegel upper half plane HG, so that's G by G symmetric matrices whose imaginary part is positive definite. And so this is a holomorphic function such that phi of gamma Tor, all right, let me call that Tor then. Phi of gamma Tor is determinant C Tor plus D to the K, phi of Tor, where gamma well, I mean, in whatever my group is. Okay, so the reason I put G greater than 1 is because if you put G equals 1, then you have to have a nicely behaved at infinity condition, but I don't need that. This. Okay. And if you do this, then you can, such a thing has a Fourier expansion. So it's a sum over, and I'll tell you what T is in a second. And then there's a coefficient A of T, and then it's exponent of pi I trace of T Tor. Doesn't really matter too much. And then this sum, these T's, these are even symmetric, integral symmetric matrices. And then the vanishing of vanishing order at the boundary is some number B, which is it's 1/2 of the essentially the smallest number that you get out from these, the minimum of the X transpose TX for which, where the t is the ones for which a of t is not 0. And x is non-zero element of ZG. Okay. So it's the smallest number represented by these quadratic forms with the for which that actually occur in the expansion with this large factor of a half. Just okay. And then a cusp form is one for which B is strictly positive. Okay. What else do I need? I need the Sataka compactification. This AG star is it's proj of the ring of modular forms in actual fact. It's a projective variety, it's quite badly singular. But what you need to know about it is that as a set, AG star is AG, and then there's an AG minus 1 and an AG minus 2, and so on all the way down to A naught, which is just a point. Okay. So one way to think of this is to say that if you've got a family of abelian varieties and it degenerates, one of the things you can make it do is degenerate. If you're not worried about properness, you can make it degenerate to a semi-abelian variety. And this index here, if you take a family that just does that in the moduli space, this index here tells you the dimension of the abelian variety part of it, and you've got a GM on top. And where you've landed in that tells you the moduli point of the abelian variety part. So you've thrown away lots of information. You don't know what the extension class was. So it's not even it's not a sensible moduli space, but it still makes some kind of sense locally. Okay. And then the Mumford partial compactification is this bit. And that's sometimes called AG dash. I'm not quite sure I'm actually going to use that notation. I'm sorry, I said that wrong. This is, say that wrong. I said that totally wrong. I'm sorry. Let me say that again. If I look at just this bit, so AG dash is this blown up along the AG minus 1. So what I get here, so this is very high, this is of high codimension in here, it's codimension G. And so what I'm doing is I'm saying, well, look, let's forget all this very low, very high codimension stuff, just look at the main boundary component, blow that up so that it becomes a divisor. And this is called the Mumford partial compactification. All toroidal compactifications have this much in. And then they disagree with one another over these lower strata. You have to make some more choices. But when you do a toroidal compactification, you're doing, one way to say it is you're doing some kind of blow up of the boundary, and there's universal agreement on what you should do at in this main stratum, because you're making essentially because there's only one way to compactify C star. It's just to put the origin back in, but then once you do this, you're trying to compactify a C star squared, and then there are lots of ways you could do that. Okay, okay. So the reason I want to do this is I want to be able to talk about the slope of divisors and the slope of modular forms, and that's determined by what goes on here. Okay, so how much time have I got? I'm not doing too badly. Okay, let's try going back to the middle board. And the other thing is, of course, because I haven't given one of the, I mean, my timing in these things tends to be bad anyway, but it's going to be worse. Okay. Okay, so for G greater than or equal to 3 now, the Picard group of this, well, at least modulus, and apart from some torsion, is of rank 2. And it's spanned by the Hodge class, the class of the Hodge line bundle, in other words, the divisor corresponding to modular forms of weight 1, whose local sections are germs of modular forms of weight 1. There aren't any global sections, but never mind. And delta is the boundary, the reduced boundary. So the exceptional thing in this blow up. Okay. And the slope of an effective divisor E so it's an effective divisor, so it's A lambda, I'm going to write it as A lambda minus B delta. So that is the same B that we had before. And I'm going to have A and B positive just to stop myself having to divide by 0, is, I'll call it S of E, which is simply A over B. So that's just a name for this ratio. And so in particular, if you give me a cusp form of weight K and vanishing order B, then the slope is just K over B. Okay, so e.g. cusp form zeros of cusp form of weight A and vanishing order B. And then the minimum slope S min of G, it's the genus, is the inf of all the slopes of I don't want to look at what happens over here, because if I start taking toroidal compactifications here, I'll introduce a lot more divisors, and then I will have trying to find cones in some high dimensional vector space, and I don't like that. Okay, so this is the smallest slope that you can get. And then, okay, so we've known for a long time how to get at so this number is a bit mysterious. We don't necessarily know what it is, but we know some bounds. Some cases we do know. Okay, so for G equals, well, 2, but yeah, I'm trying not to talk about 2, then, and 3, the minimal slope is, well, I'll say what it is for 2, it's 10, and this is given by the thing called theta null, which is the locus where so theta null is the locus where, if you think of this as modular of abelian surfaces threefolds, this is the locus where the theta divisor has a singular point of order 2. G equals 4. S min of 4 is 8, and this one is given by the So this is the Andreotti-Meyer, well, it's the other component of the Andreotti-Meyer locus, if you're used to that. It's the things where the theta divisor has a singular point not of order 2. So this is, so these are things that come from the geometry of the abelian varieties and how they're parameterized. And then dropped everything on the floor. Yes. I mean, because if you're a number theorist, you'll try and write down Eisenstein series, for example, which will never do that. And then for G equals 5, S min of 5 is 54 over 7, and these are both n naught dash equals theta divisor has non-double points. I mean, singular points of at least 3. Okay. So the beyond that, it gets kind of more difficult to say what's going on. And I will say what we know, and then yeah, okay. Then I've got just about time to say what we have to do to make this all work. Okay, and then for G equals 6, then this is actually less than or equal to 7. And this is actually very recent. Dittmann, 2 ends. And so this is a recent result of Dittmann, Nils Scheithauer, and Riccardo Salvattimani, and this is actually what tells us that the Kodaira dimension of A6 is not minus infinity. But we don't actually need that. But I mean, essentially, this started because we knew this fact, and we wondered, what does it prove about these Kodaira dimensions? And actually, it doesn't prove anything that we didn't know without this fact, because turns out. This is done by finding them not uniform and just checking its vanishing. Yes, and the checking its vanishing, I mean, you find out what the, I mean, it turns out that the thing that really that it comes down to is that somehow it's associated with the Leech lattice, and and some of the order of the vanishing is controlled by the number of roots, the number of -2 vectors. The Leech lattice hasn't got any of those, and that gives you the right thing. I mean, obviously, it's. Sorry, your remark about A6 is just you found them module 4. Yeah, they found. In fact, what they found is they found a section of 2K. I mean, I haven't, no. But it's actually, this is less than 550 over 73, which is less than 8. And that comes from, it's n0 or n0 dash. I remember it's n0 dash. Same one as before, in other words. It's less than 8 anyway. So we knew it was less than 8. It's actually less than or equal to 7. So this fact is critical for thinking about A6. And so we actually embarked on this because we thought it might be critical for thinking about AGN as well. Turns out it isn't. It turns out we could have done this earlier. But also because we have this fairly new results of Mars. So people were looking at this sort of thing. Okay. So I mean, I just need to tell you what the connection is between S min and Kodaira dimension. And so, the theorem is if G is greater than or equal to 3 and is what I was calling a Namikawa compactification. So that means that it's a toroidal compactification in that sense that it maps to a toroidal compactification, and it's not got and it doesn't do it by contracting divisors. So it's a Namikawa compactification with canonical singularities. Okay, so I'm trying to do two things at once here, and they're going in opposite directions because the so if I want canonical singularities, I can just I can blow up a bit. I mean, I could even get something smooth if I wanted to do that. But this Namikawa compactification condition says, no, you mustn't do that, because then you'd be getting divisors contracted to the things you blew up from. So it's not a priori obvious that you can do that, but suppose you can. Okay, and in that case, then the Kodaira dimension is half GG plus 1 if, and you just work out what it is, if S min is less than G plus N plus 1, 0 if S min of G is equal to G plus N plus 1, and I need D to be rigid, since it doesn't move in any linear system. It's isolated. It's the linear system D is just the one point. So H naught of this is 1 or 0, and then so this is again a 0 and then minus infinity if S min of G is greater than G plus N plus 1. So of course I can now compute all of these things, and it gives you what you want. So this first one, this is basically just Mars result reinterpreted, you just write down. So what Mars result says is that if you at least if n is sufficiently divisible, it tells me that nkx is and then it's mg plus n plus 1 L minus m delta x, and so that just gives me this result, as long as g plus n plus 1 L minus delta x is big, but it is, because it's got slope bigger than S min. So it's in that cone. It's in the interior of the effective cone. That's really what it comes down to. So I mean, Mars result tells you the slope of the canonical bundle, and this tells you that slope is in the interior of the effective cone. This tells you it's not effective, and this one tells you that it's big, but sorry, it tells you that it's effective, so you just count sections. Okay. So the main theorem that I wrote over here, did I remove it? That's just a restatement of this. So my remaining assertion, which I'll try and sort of explain something about in the last few minutes, is that that compactifications like this actually exist. So that's the new thing that we have to do. I mean, this is all just rearranging things that we already knew. So what I need to do is to establish there is a Namikawa compactification with canonical singularities. And as I said, this is not a trivial thing to do in principle, because the two push in opposite directions. Okay. So which order do I want to do things in? So, I mean, how do you go about proving that something like a toroidal compactification has canonical singularities? Well, your first thought is to say the moduli spaces we're looking at are quotients by some discrete group. So they'll be smooth except where there are fixed points. And then you look at the fixed points, you linearize the action on the tangent space, and you use the Reed-Sheppard-Barrentai criterion to find out whether see whether the eigenvalues add to 1 or not. Logs of the eigenvalues add to 1 or not, the age. So this is a kind of well-known thing, but you have to do a computation each time. But that's for something that's acting on a smooth space. Now I'm trying to get a compactification, so when I do a toroidal compactification, I still have locally what I have is I've taken a piece of the variety which looks like some irrelevant stuff cross a torus. I've replaced that torus. I've chosen a particular cusp, and I've gone there and I've replaced that torus with a particular toric variety. And the stabilizer of that cusp is still acting there. The stabilizer inside gamma of that cusp is still acting there. And so the cusps are, that's a cusp and that's a cusp and so on. So I've got one for each. G dash goes from 0 up to G minus 1. And then I've got to look in the tangent space of that and see what happens there. But I have a choice of what toroidal compactification to take. I mean, here I haven't, but as I go further into the corners, I have a choice of, I have to choose a fan and choose a toric variety. So I should say the toroidal compactification, obviously it isn't saying that the variety is globally something or other cross a torus, because I'm telling you these varieties are something like general type, so they obviously aren't. But they have an open piece in the Hausdorff topology, which can be identified with an open piece of a toric variety. So locally, if I'm just looking at it's still a matter of looking at a discrete group acting and then acting with finite stabilizers, and so you still need to look at that. But I don't want to choose so what you tend to do is you say, well, okay, let's take this toric variety to be smooth, because then you have a nice, you can tell what's going on. And then you can say, well, okay, we'll do that, and then we can apply the Reed-Tie criterion and Sheppard-Barrentai criterion. We can find out whether the singularities are canonical or not. We're either in luck or not. The trouble is that in order to get a smooth covering space near each cusp, I've had to do masses of blowing up. And in the process, I violated this condition. What lets me out is the following lemma, which I was going to prove for you, but I think I won't. So the lemma I'll try and state it in exactly the way I've got it stated here. So suppose that G is a finite group acting on a variety Y, and the Y has canonical singularities. Sorry. And I need one other thing, which is that I need that no element of G, no non-trivial element of G preserves a divisor. So with no fixed divisors. Okay. And then let's have a G equivariant resolution of singularities. And suppose that y hat mod G has canonical singularities. And the conclusion is that then y mod G also has canonical singularities. And essentially, you do this by just pulling differential forms around it. So just do it by hand. Okay, so the reason that this is useful to me is I'm going to be able, although I have no time to do it, I'm going to be able to write down, what it allows me to do is to say, when I choose my toric varieties to patch together to make my toroidal compactification, if I choose those to have canonical singularities, I don't need to choose them to be smooth. I only need to choose them to have canonical singularities. Then I can take an equivariant resolution of those, and I can check the Reed-Shepard-Barenthal criterion up here, and that's just as good. Right, so what I need to do is I need to produce a compactification of XNG, toroidal compactification, where the toric pieces have canonical singularities. Okay. So it's enough. Well, it's not enough. I still have to check the Reed-Shepard-Barenthal criterion, and that's where Flora came and told us what we were doing wrong when we tried to do that. So that's why things have changed since February, because we got that computation. We made a mess of that computation, and Flora was able to tell us what mess we were making of it. Why it was. So it's enough to find a compactification and a Namikawa compactification. In other words, one where I'm not putting in lots of new divisors I didn't know about. With canonical singularities on the toric varieties. And that's before taking the quotient by the stabilizers. So it's built out of toric pieces, and then at the end you take a quotient by some group action. But as long as I have canonical singularities there, it was enough to do that and check the RST criterion. Okay, so how do I do that? Well, if I were trying to do this with AG, then I know how that's done, because the first Voronoi, or perfect cone compactification, does that for you. And it does it. The reason is what you're doing is you're looking at the cone of positive. You're looking at the cone of positive spanned by positive semi-definite rational quadratic forms. So that's all the positive definite quadratic forms, and then some rational stuff around the edges. And it is the theorem of Barnes and Cohen tells you that that's actually when you take the convex hull of the rational points, and that's the same as taking the convex hull of the rank 1 forms. So it's the convex hull of something. That's really all I need to know. It's the convex hull of the integral points in the lattice of integral quadratic forms of that kind. That's what you do for the so this is called the first Voronoi. Does this for AG. And then to do it for XGN, what you have to do is you're now looking at a kind of extended cone where you're looking not at quadratic forms, but you're looking at quadratic functions. So they've got a quadratic part, but they've also got a linear part, but modulo the constants. I'm being a little imprecise about this because there are n of these linear parts. But anyway, it's essentially it's sim2 of some lattice, direct sum n copies of that lattice or n copies of its dual. The cone lives in there. And what you can do is essentially the same trick. You take the convex hull of all the forms of that type, the functions of that type, whose quadratic part, the degree 2 part is of rank 1, the integral ones of rank 1. And you have to check, I mean, there's a little bit of checking that you have to do to check that, yes, that really is the right thing. But the point is I didn't have to do any cutting up. I mean, it gives me something, I mean, I didn't say that these were Q-Gorenstein, well, Q factorial, they're Q-Gorenstein, but they're not Q factorial in general. I don't expect the cones to be simplicial. Okay, and so, so this, I mean, actually, this is kind of implicit. So in the book of Chaienfaltings, they very nearly do this. They say they're going to do it, and then they don't, but you can. And then you have to, check the Riesch-Shepard-Barantai criterion. So you write everything out, and then you get it wrong, and then your research student comes and tells you what you've been doing wrong. That's how you do that. So I'm not going to go into that. I've over time anyway. Let me stop there.
Any questions? If there's any questions online, if you post them in the chat, I can read them out. Now somebody's ringing me. Hello?
Yeah, it might have been pinged, I suppose, or maybe wants to say we couldn't hear a thing. Or
if there's any questions, Alan's not there, but I can read them out. Any questions from the audience?
no, I either made complete sense or total, no, or nobody understood a thing, one or the other.
So let's thank Gregory again. Oh, you have a question.
Say a few words about what color is it?
Yeah, well, I mean, so if you want to check this RST criterion, so a point, because of the way that the Namikawa compactifications work, if I have a point in X in XNG bar, then it maps to some toroidal compactification of AG, and then that maps to the Satake compactification. So it lands in one of these strata. And you have to deal with each stratum separately. You know, so you get a description of the tangent space of the space with the tangent space to the covering space where the stabilizers are acting, and it breaks up according to this. So there's a part that comes from the tangent space to this, which is the same as the tangent space to HG. So if I call this G dash, then there's a part that comes from the tangent space to AG dash, and then there's a part that comes from the lattice that I was just describing. So it's G dash. So G double dash is G minus G dash, and then the cones live in that space of quadratics plus together with n times linear, n lots of linear things in dimension G dash, and then there are some kind of cross terms that come in. Really what happens is you try and analyze these, and you get down to a few cases that are potentially troublesome. And the one that was particularly troublesome is if you take G dash equals 1, so it's living over, so so there's an elliptic curve in the picture somewhere, and that elliptic curve has J invariant 0. So it's got a symmetry of order 6. And then you get, so potentially you then get singularities of the form 1/6, 2, 1, 1, or 2, 1, 1, 1, and then lots of zeros, which are non-canonical. And so you count this bit, and then you count what comes from that lattice, and then you look at the cross terms. And really, what happened was that I convinced myself that the cross terms couldn't give me anything useful because I couldn't exclude the possibility that the eigenvalues you get there are all just 1, which wouldn't help me any. Flora's more careful than I am, and she took it to pieces and found that actually that can't happen. And in the cases that we're interested in, the eigenvalues that show up actually cannot all be 1, and that's enough because you get an extra 1/6, which is enough. So that's the specific. That's the specific thing. But more generally, I mean, I just tried to explain this to her, and she said, "Well, you should look at it more carefully." So, I mean, it's joint work. I mean, we talk to one another. That's not to say that everybody talked to everybody about everything, but it's so she made us do that properly, and she did it herself properly. So that's I mean, I don't like breaking joint work up and say, he did this bit, she did this bit. It's not really like that. But in this particular case, because I'd already talked about a version of it, I didn't have Flora's name in it. There's some reason to ask that question and some reason for me to answer that question. But joint work is joint work.
Any other questions? There's no question coming from the chat. No more questions. Let's thank Gregory again.
How do we adjust the volume on the microphone? Camera capture.
On the right of the screen.
Here we go.
I turned it down a bit.
Say something.
Say something.
Hello.
Is that
Is that okay? Can you hear me?
Yes, I think you're probably allowed to lecture the mask off. I did.
Yeah, you can.
Yeah, okay. Yeah, that's good.
Oh, that's better, isn't it? We can hear it. Yeah.
Look.
I'll put your camera controls back. Okay, hello everybody. Welcome back. I should go and stand in front of where the camera is. So our second talk today is Anna Peón-Nieto from Birmingham, and she's going to be telling us about wobbly bundles and applications.
All right. Thanks. Thank you for the invitation. It's a pleasure to be here. So as I was telling Alan before, I've been a little bit ambitious about the title. Let's see if I get to the applications, but at least to wobbly, I should be fine. So wobbly bundles are no acquaintance of the theory of vector bundles. They've been there since Lamont's work in the 80s, but they are back they're trendy again because of Donaghy and Pantev's program to prove geometric Langlands from abelianization of Higgs bundles. So I'll start by the basics, present all the characters, introduce all the characters, and eventually I will get to the definition of these guys and speak a little bit about what role they have in the current arena. Right, so let's start by Higgs bundles. Is this big enough? Yeah?
Okay.
A bit bigger?
Not any smaller.
Okay. All right, so let's fix X a smooth projective curve of G over C, always C, of genus at least 2. So if you like surfaces, Riemann surface is better, so a donut with at least 2 holes. And so a Higgs bundle on this curve is given by a pair of objects I'm going smaller, by a pair E, which is a holomorphic vector bundle on the curve, and phi, which is a holomorphic endomorphism, but twisted by the canonical bundle, or if you prefer, the holomorphic cotangent bundle. So this is canonical. So that phi can be seen as an endomorphism of E phi twisted by the canonical bundle. Okay, so these objects actually, well, up to a condition, behave well in families. So there is a scheme, which is the so-called moduli space. So I'm going to denote it by mx, and I'll have to fix some invariants to have the non-reducibility. So this will be the rank of the vector bundle, and this will be the degree. So the closed points of this scheme are pairs of Higgs bundles, which satisfy a certain condition that I'll define in a minute, which is semi-stability. And they are classified up to isomorphism, although this is not quite true. It's true for smooth points or, in fact, stable points of the moduli space. So a semi-stable Higgs bundle is the following. So if for every Higgs subbundle, that is every subbundle, that's not the whole thing and not zero. So Higgs subbundle means that it's left invariant by the Higgs field. The slope of F, which is defined to be the degree of F, quotiented by its rank, is smaller for stable, or equal is allowed in case of semi-stable than the slope of E. In this case, since I fixed the invariants, this is just n divided by n. Okay. So an example is the case of rank 1, which is simple, because there are no subbundles that are non-trivial.
Sorry.
Yeah.
Your camera's pointing at the right hand.
Oh, so I'll just move. Thanks for preventing. So in the case of rank 1, so we have the moduli space of, say, rank 1 degree whatever Higgs bundles is just the cotangent space of the Jacobian variety of bundles of degree D. Right, and this is just because, well, given any line bundle, the only subbundle that's non-trivial is that's non-zero is itself, and that's not allowed. So it's just stable. And this is just the Jacobian times holomorphic differentials. Okay, so although, this is a very nice, at least geometrically speaking, example, and this, of course, is not true in general, but what happens is that for arbitrary rank, can you see here? The cotangent space to another moduli space, which I will explain in a minute. So this is the moduli space of vector bundles. of degree D and rank n. So the cotangent space to this modular space, or in fact its smooth part, is dense and open in the modular space of Higgs bundles. So part of the Nash geometric properties that are satisfied by the modular space of Higgs bundles comes from this fact. So for example, this is a holomorphic symplectic scheme, and the symplectic form is just a very natural extension of the canonical symplectic form of the cotangent space. So let me remind you. So actually the modular space of vector bundles is defined. I mean, the closed points are very similarly defined. So we would have the closed points are semi-stable vector bundles. And again, it's essentially up to isomorphism, or at least in the smooth part. And semi-stability is very similarly defined. So we just omit the condition that the subbundle needs to be preserved by anything, because we don't have a Higgs field, right? So E is semi-stable if for every non-trivial subbundle, the slope, so this is subbundle. The slope of the subbundle is smaller than or equal to the slope of E. So a remark is that the stability notion for vector bundles is much stronger than stability for Higgs bundles, right? But I mean, a reasonable question is that all? I mean, is there something else? Well, the answer is yes. So the modular space of Higgs bundles has more objects than like cotangent vectors to the modular space of bundles, and many more, in fact, because well, many. This is not the only thing that's interesting. I'll say more in a minute. So, for example, yeah. Into what?
Into map 5. And clearly, what you're saying is
yeah.
cotangent bundle to the ordinary bundle, the sequence at Higgs bundle. So somehow the cotangent
yeah.
information that basically that map. So,
yeah. Yeah. So the tangent space, to a vector bundle of the smooth lockers, it's one of the endomorphisms of A. These are the deformations. So Serre duality gives you, but that's fine.
But it may be worth saying T star. The T star means dual vector space.
Yeah.
It doesn't mean that you tensor the origin.
Yeah.
So the Higgs field is allowed to be 0, or is allowed to be 0 on submatrix.
Exactly, it is allowed to be 0 indeed. Mm-hmm. Right. So an example of something that's not in this cotangent space is the Hitchin section. So if we take this vector bundle, it's not stable. It's not even semi-stable, right? Its degree is 0, so its slope is 0, but it has a subbundle with positive slope. So, but it can be made stable as a Higgs bundle just by taking the following Higgs field. So you map everything to 0, except whatever is messing about is messing up the semi-stability that you can send to this line bundle tensor by the canonical. So let me write things a bit more explicitly, right? So I'm taking the image of k minus 1/2. So this is going to itself tensor by k, or to k3/2. Yeah, right. So I can send this one to the other one by just the identity. And it becomes stable as a Higgs bundle, right? So what I'm saying is that the locus of Higgs bundles, which are semi-stable, so points in the moduli space, but such that E is not semi-stable, non-empty. And in fact, it plays an important role in Donaghy-Pantev's program. Okay. So I mentioned before that there are some important consequences of having a cotangent bundle being dense and open. And one of them is the symplectic structure the moduli space inherits. So great. So some consequences. So one is there exists a holomorphic symplectic form. So of course, this moduli space may have singularities. It is defined on the smooth locus. Omega, which acts by serduality. So the tangent space at some point is H1 of the endomorphisms. And so yeah, I mean, this is just yeah, sorry. So I mean, tangent space to a point of the Higgs bundle moduli space is something like right. So serduality defines a pairing. Yet another consequence is the fact that there is a rational map from the moduli space of Higgs bundles to the moduli space of bundles, which in fact is surjective and also plays an important role in Donaghy-Pantev's program. Okay, so the last important feature about the geometry of Higgs bundles I'm going to need is the Hitchin map. In fact, endows the moduli space with a completely integrable system structure. So this is just the characteristic polynomial map in this setup. So it sends a Higgs pair to the following. So for now, this is some formal object, but it makes sense to consider such a characteristic polynomial because the coefficients are adjoint invariant polynomials, and so they can be evaluated on the Higgs field. So what one gets is sections of different powers of the canonical bundle. So the trace gives a section of the canonical bundle and so on until one gets to the determinant, and then this will be a section of the nth power of the canonical bundle.
Sorry, that's K times I.
Yeah. But it can also be interpreted geometrically.
Vector space.
Sorry, say that again.
This is a vector space.
Yeah, it's a vector space.
You're not using the multiplication.
Well, I mean, here I'm choosing a basis of the invariant polynomials. I could have defined it more invariantly. Yeah, I mean.
But it's a finite dimensional vector space.
Yeah, exactly. All right, which side? No. Okay. Right. So in fact, this can be realized, this characteristic polynomial can be realized as a section of a bundle on a surface, which is just the total space of the canonical bundle. All right. So say take the total space of the canonical bundle, which comes with a map to X. And here we have the vector bundle given by the canonical bundle itself. So pulling back, we have a canonical section, or tautological section, I guess it's called. And so now this object does make sense. Okay, this will be plus minus, but let me not be bothered. So this is a section. So the B's are the image under the Higgs map of any Higgs bundle having phi as a Higgs field, or I mean any Higgs field which has the same invariance, of course. And this can be realized. So this is a section of the nth power of the canonical bundle, so the pullback canonical bundle on this surface. So this defines a divisor, which is the spectral curve. Maybe I'll continue the next one. So it's a spectral curve, and it parametrizes, of course, the eigenvalues of the Higgs bundle. So say XB, it only depends on the invariance. It's a curve inside the surface. And it's an n-to-1 ramified cover of X. So it's ramified because already, if we think about rank 1, what is a Higgs field? Well, it's a section of the canonical bundle. It will be nilpotent at some point. So at some point, the eigenvalues will collapse. But it's generically smooth. The beautiful fact that Hitchin discovered is that the generic fibers are in fact isomorphic to the Jacobian of the spectral curve. So this is it. They are moreover Lagrangian. So for B generic. And of course, smooth when B is generic. All right, but today we will not focus on generic fibers. We'll rather be talking about the the least generic of them all, which is the nilpotent cone. So are there questions so far?
Is that for fixed E?
This
E is a given Higgs bundle.
in here. Well, I mean, I'm defining the map, but for a given point B, there will be different E's that appear in the pre-image. Like, for example, the Hitchens.
X is the curve.
X is the curve. XB is the spectral cover, yeah.
Depending, so is that as E varies through all Higgs field, all vector bundles and all Higgs fields?
So I'm fixing the characteristic, but
Oh, okay.
yeah.
So it's the fiber of the Hitchin map.
This is the fiber of the Hitchin map. That's right. Yeah, yeah. Okay. All right. So the nilpotent cone is particularly important in the study of these moduli spaces because it encodes, say, the geometry of the moduli space of bundles for a very simple fact that I'll state in a minute, but also the moduli space due to the existence of the, sorry for the pronunciation, but I don't know how to do this. The Bialinici-Berula, that's again wrong. Stratification. Also known as the nilpotent cone or the global nilpotent cone, as Lomo called it. So we remarked before that the moduli space, so the stability notion on vector bundles is way more strict than the one for Higgs bundles. So in fact, one can embed the moduli space just by sending E, so as Miles observed before, to E0, right? And this defines an element of the moduli space of Higgs bundles, but obviously it is nilpotent. So in fact, strictly speaking, it's, I mean, I should say the reduced scheme underlying the nilpotent cone, because all the irreducible components come with multiplicities. So the nilpotent cone is really non-generic, so it's reducible. It's non-reduced. But it has also some nice features, so it's also Lagrangian. And it's of pure, well, it's Lagrangian, of pure dimension, in fact. Obviously 1/2 of the dimension of the moduli space. This is bad, right, Alan? Yeah.
In what sense? It's fine. I
It's
can
fine.
read it.
Okay. Right. So I'm fine. So now the sister action allows to contract the whole moduli space to the nilpotent cone. So we have so here we have the base. nilpotent cone. So let's start by any Higgs bundle. So I can act by C star just by multiplying the Higgs field. And then since the Hitchin map is proper, I can take the limit as t goes to 0. And this flows thanks to the nilpotent cone, because if one works out the appropriate C equivariance condition, well, the Hitchin map is C equivariant. And although the action on the base has weights, it's still given a homogeneous polynomial, so it's 0 on 0. Right? So the flow will hit different components of the nilpotent cone, which are fixed point components. So one of the fixed point components is the moduli space of bundle itself with whatever multiplicity. But there are others. So if we picture the irreducible components, we could have started by something that's non-smooth. So if this is smooth, it will flow to a nilpotent cone. Sorry, to the moduli space stable. Sorry. Unstable, but we could have started with something that's unstable, like the Hitchin section. Okay, sorry, defined before. So one can still do the same maneuver, but in this case, it will flow to a different component of fixed points, which is not in the moduli space. So this is as t goes to 0. And similarly, in the nilpotent cone, we can start by something in an irreducible component, multiply by t. And it will flow either to the moduli space at 0, if, of course, the underlying bundle is stable, or somewhere else if when we go to infinity, regardless of the semi-stability condition of the bundle. So why can I mean, in this case, we can flow to infinity because it's, again, the Hitchin map is proper, and so the fiber is also proper. All right, so Lomond studied, I mean, not only Lomond, Drinfeld, Ginsburg, many other people studied the geometry of this variety. And one of the things that they realized is that the downward flow from the nilpotent cone hits a non-generic locus of the moduli space. So I'm cheating because his focus was not on these non-generic locus, and he did not talk about them sister action, but I'm translating, say. So we can now define what wobbly is. So vector bundle, or rather, let me define very stable. A vector bundle E is very stable if it has no Higgs bundle that's non-zero and that's nilpotent. This definition is Drinfeld. So there are two things that Lomond proved. If E is very stable, then it is stable. So notation, the very stable locus of the moduli space is going to be denoted by this. And also, the very stable locus is dense and open inside the moduli space. But in fact, our focus is rather on the complement. So this is the wobbly locus. All right, so the very stable locus is clearly interesting. I mean, it's dense and open inside a moduli space, so one can deduce a lot of things about the geometry. But according to Drinfeld's announcement conjecture, so the proof is not available. He claimed to have proven it. It is of pure codimension 1. Right, so it defines also a geometrically interesting object per se, not just because it's the complement of this large set. So I'll speak about this in a minute, but let me mention another conjecture by Donaghy and Pantev. So the wobbly locus, as I mentioned, that it appears in their program towards geometric Langlands through abelianization. So if I have the time, I'll talk about that too. So they claim that the wobbly locus is the shaky locus, which is, I mean, it's, let me just wait till the end if I get the time, but this hand-wavily speaking is the locus of the moduli space of bundles over which the Higgs bundle explode in a sense. So we would have this rational map I mentioned. And here we would have some shaky locus over which there are no Higgs bundles. It's not defined because the corresponding bundle should be unstable. Okay, this is very not concrete. Hopefully I'll be able to say some more in a moment. Right, so Drinfeld's conjecture, let's say conjecture, was proven in rank 2 by Pal and Pauli. This is the okay. So in rank 2, it was proven by Pal and Pauli. So let me remind what they did, because it will be useful for the sequel. So there's a crucial remark. Because it is the geometry of the nilpotent cone that gives us the hint to understand how to try and prove this conjecture. So if one looks at one of the non-moduli, say, so an irreducible component, what one sees is that we have Higgs bundles flowing down, Higgs bundles flowing down to the moduli space of bundles. Right? So by definition, the wobbly locus are those bundles which admit a non-zero Higgs bundle flowing down to them. This is a bit trickier when it's strictly semi-stable, but they will be in the closure anyhow. So let's think of things of stable guys. Okay, well, these components, or at least the reduced schemes underlying them, are Lagrangian, and they are smooth. And so what one can prove is that if we have, say, E0, and we have a Higgs bundle flowing down to it, phi, the space generated by phi is contained in the normal space to, let's say this is C, an irreducible component. It will be determined by some invariance, let's say Ci. And let me call Wi the intersection of Ci with the moduli space. So this is a wobbly locus, maybe not of codimension 1, but what it's for sure is that since this is contained in the normal space to the wobbly locus inside of Ci, then we want to look for those bundles which admit just a Higgs bundle, at least in one of the components. Is that clear? Sure. Should I explain more? Or? So the strategy. So if for a generic point, there exists a unique Higgs field which is nilpotent, well, up to homotopsis. Then Wi is a divisor. Okay. So that's the strategy to prove. So there will be, in fact, what happens is that there are some irreducible components for which this holds, some others for which it's false. So the components of the nilpotent cone collapse to lower dimensional subsets, and those can be seen to be contained in codimension 1 wobbly loci. Okay, so let's fix ideas for rank 2. So this is due to Pauli. Okay, so let's start with a Higgs bundle that's nilpotent. So what this means is that phi induces a filtration on E, which is the iterated kernel filtration. In this case, it's just the kernel, right? We have the kernel of phi, which is contained in E. Okay, so a remark is that the Higgs field is totally determined by a section from F1 to F0, okay? Right, so right, just by definition, because this is the kernel of phi. And so we see that through an nilpotent Higgs bundle of rank 2, we've produced 2 objects. So we have the kernel, and let's take this other element. So this line bundle has a section, right? So let me write it this way. So it belongs, one belongs to the picard of a curve, and the other one belongs to, let me be a bit pedantic and write the Brill-Netter locus of rank 1 and degree delta. So delta so di is the degree of Fi. So what is the Brill-Netter locus? Well, this is just line bundles with a section. This is the symmetric product of the curve if delta is smaller than or equal to g minus 1, and it's just the Jacobian otherwise. Okay. Right. So let me call this Z11 delta. So we have a scheme. And what happens is that E phi can be totally recovered by considering Higgs bundle extensions of F10 by F00. Right, so to recover E phi from those, what we need is a section of O of that bundle. And an extension bundle of F1 by F0. So this is equivalent to taking Higgs bundle extensions. So we have F10 and extend it by 0, 0. And this is there is a the hypercohomology of a complex parameterizes these extensions. So in this case, the complex is very simple. It's just complex given by F0, F1. So this is my complex C. Maps for 0 to F0, S1K. So if one writes the long exact sequence defining the hypercohomology, one sees that all we have is just an extension and a section of the line bundle I just mentioned. Okay, so remark. So in this case, it's a bit of a pedantic way to put it because it's not necessary. It's a split complex. So this is just H0, F0, F1, K plus H1. Okay, but it turns out to be the right way to put it if one wants to generalize to higher rank. So the theorem, my pardon, is the following. The components, irreducible components of an important cone are classified by the invariant delta there, which varies between 0, no, equal, and 2g minus 2. So, of course, delta has to be congruent to the degree modulo mod 2 to make sense. Okay, so for each delta in this range, the corresponding component will be non-zero, and they are given so they're birational to some projective bundles over these Z I just wrote. So they are the projective bundle associated to some vector bundle. So it's a bundle over Z delta 1, 1 with generic fiber H1 of the complex associated to the given point of Z. So the complex generically will have, so these will have generic rank, constant rank, and therefore, as a vector space, it doesn't change. Okay, so the tricky point here, well, is to prove that there exists a rational map to the moduli space of bundles. This just adds to, this amounts to proving that one of the extensions is semi-stable. And then the most interesting part is the fact that the wobbly loci are not always of pure codimension 1, but so what I was saying is that they are given by the closure of some rational map. We have a rational map from these projective bundles into the moduli space, taking the closure, one gets an irreducible component of the nilpotent cone. So the wobbly loci, the wobbly locus is the union of W delta 1, 1, where delta varies at this time between 0 and G. And it's defined as before, W delta 1, 1. It's the corresponding component intersected with the moduli space of rank 2 bundles. Okay. All right. What time is it? How long? I have what, 10 minutes?
About 10 minutes, yeah.
Yeah, okay. I better rush. Okay. So in the remaining time, let me speak about rank 3. So this is joint work with Christian Pauli, and our aim was to establish some recursion system in order to construct components of the nilpotent cone from lower rank components, and likewise for the wobbly loci. So we see this in rank 3. So right. So what happens for higher rank? Well, in higher rank, there are more kinds of nilpotent Higgs fields, right? We could have that the square is 0. That's very similar to rank 2. There will be a kernel. So the infiltration has only 2 steps. So we have, again, that E0 is an extension of some rank 2 bundle, in this case, by some rank 1 bundle, sorry, the other way around, a rank 1 bundle by a rank 2 bundle. But it could also happen that the cube is 0, but not the square. And in this case, the filtration is more complicated. So let me call the iterated kernels by EI, and FI will be the graded. Okay, so very briefly, what I said about rank 2 essentially translates to the first type of bundles. So there's a little, I mean, there are some technical complications. For example, F0 could be unstable, but one can rule this out generically. So we need not take care of that. This follows from the work of Lemon, who proved that say the length of the filtration and the degrees of the graded objects give a certification. And the way this certification specializes rules out the fact that F0 can be generically unstable. This is the first difference. And then it's a bit trickier to prove that that rational map exists, but not very much. I mean, this follows from Russo-Teixeira. So, okay. Let me write it in rank 2 and rank 3. Phi squared 0. Okay, so we have that from F0 and F1. 0k, which was an element in the Picard times the Brill-Netter locus. We could recover the Higgs bundle just in terms of Higgs bundle extensions. Well, the same happens here. If we take a rank 2 bundle and if we take a nilpotent Higgs bundle like that, it turns out that the Higgs field is equivalent to having a map from F1 to F0k. So that this guy here is in the corresponding Brill-Netter locus, and generically it will be stable. So in this case, we have a rank 2 bundle, D0 times a bundle with a section. In this case, it's rank 2, and delta, saying now is the degree of this guy. Delta equals 2 0 minus 2d1 plus g minus. But then it's the same. We have a bundle over Z. The generic fiber given by Higgs bundle extensions of F10 and everything goes through with a little bit of extra work. It's also true that the wobbly loci are not of maximal codimension for all invariants. So roughly half of the invariants give irreducible components of the wobbly locus. Right, so the length 3 filtrations are more complicated, and in fact, we don't completely understand them yet. But there has been progress since the last time I spoke about this, I think in Nottingham, it was. So very briefly, I don't know what it's 2, okay. Rank 3, 5 cubed equals 0, 5 squared. Right, so in this case, there's a Q remark, which sets off the recurrence. So if we start by nilpotent Higgs bundle like this, it turns out that the kernel, so think of it locally if you want, so we will have something like that. Okay, so this is E0, this is E1, so the kernel of phi squared, this is E of course, and let me call this Q0. Okay. So we see that E produces 2 wobbly guys, which is the kernel of phi squared with the induced Higgs bundle. And the quotient of E by the kernel of phi with the induced bundle. It's not hard to see that phi induces a Higgs bundle that's nilpotent, a Higgs field that's nilpotent on Q0. So these are both wobbly and possibly nilpotent. Sorry, unstable. So now the idea is to recover E from elements of this kind satisfying the right relations. So far what we have is the following. So obviously E1 is an extension of F0 by F1, and Q0 is an extension of F1 by F2. That's the notation. So what we see already, the first condition is that the kernel of phi 0 bar has to be the co-kernel of phi 1. Let me denote by the components of the nilpotent cone. So there will be 2 components of the nilpotent cone. Suppose that everything's semi-stable, which need not be, but it extends to the unstable guys. So by this I will mean pairs satisfying this property. This is the pic here. Is that clear? Right, so what I mean is that the kernel of phi 1 and the co-kernel of phi 0 are the same. But in fact, that's not enough to ensure that these 2 nilpotent guys extend or say lift to a rank 3. So let me state what we have so far and then I'll finish. So take points there. So E1. So such that. So what I want is the kernel of phi bar 0 equals the co-kernel of phi 1. This is that. And I also want that by the way the components of rank 2 are parameterized, these can be thought of an extension type with some extra data. So E1, which is the extension type of E1 as an extension of F1 by F0, cup product with the divisor associated to F0 plus Q0, which is the extension type of this guy in terms of the co-kernel of phi bar 0 by its kernel. Cup product with the divisor associated to F1 is 0. So when this happens, and this seems a bit ad hoc, but it's not actually, it's a very natural analysis of thinking of E in terms of an extension in two ways, of F2 by E1 and of Q0 by F0, and see what properties have to be satisfied. Yeah, it's a very natural condition. So if one has this subscheme, then there exists a vector bundle. So it depends on two parameters, delta 1 and delta 2. So it's actually a rational vector bundle over SC with generic fiber, which is, it's contained, I mean, it's a subbundle of H1 of C, whatever complex, let me not give any more details, but this parameterizes extensions of the form, say, F00. Okay. And why is it a subbundle and not the whole thing? Well, because it's not enough to have an extension like this. It has to come with some extra properties. There need to be another wobbly bundle, which gives you the same Higgs bundle in the end. So, right. So to finish, so what happens there is that the projectivization of such bundle has a good dimension. It's 19 minus 8, which is the dimension of the Newton cone of rank 3. What we haven't proven yet is that there's a rational map. We don't know if there are semi-stable extensions in there. That's very important to prove that they actually parameterize the irreducible components. We've also identified the range in which this should vary in order to give semi-stable guys, and also have an hypothesis for which wobbly loci would be of pure codimension 1, and have proven it in a sub-range of that. But I think my time is up, so let me finish here. Thank you.
Any questions? People online can ask questions in chat and I'll read them out.
Is the inverse conjecture true in higher rank?
Sorry, can you say that?
Obviously a conjecture, but do you believe that it's true?
Yeah, I believe that it's true. Probably he's got some conceptual proof, but for some reason it's not available, but yeah. So for example, for filtrations of length 2, the same philosophy goes through again. Also for full flags, for phi n equals 0 and non-zero for the other elements. And the hope is that we can actually reduce everything to pairs. So we don't need to actually take, tripoles of Higgs bundles, just pairs, sufficiently nice, and then recover all the components.
So the hardest cases are when there's a Jordan graph of maximum size.
Well, in rank 3, yes, but I'm not sure. Like, for example, if you go to higher rank already, you can have filtrations of order 3, and there you can have phenomena when you have higher rank, because line bundles are easy, right? But higher rank, if you have a block that's of higher rank, you can have phenomena such as instability, and there are.
For example, two bundles in rank 2.
Mm-hmm. No, that's easy. The when it's just length 2, that's easier because it works essentially like rank 2. Because in that case, if you have an unstable bundle, then it's automatically wobbly. So you would have a refinement. It's easy to see that you have a refinement of the filtration, and that cannot be generic. So
like that's a question you should ask after the talk was no, it's fine.
Okay, so I'm not going to stand up this time. Yeah, so our final talk of the day is Tom Duckett from Durham, and he's going to tell us about the three-dimensional Lineus map and a self-mirror log Calabi-Yau threefold.
Okay, well, thanks for the invitation to speak, and it's nice to see people in person for the first time in a long time. So, yeah, so I'm going to talk to you about log Calabi-Yau varieties and one threefold example in particular, which is very pretty. But so in order to kind of motivate it, let me just give you start with some discussion about log Calabi-Yau varieties and why they're so interesting. So let's say, so a log Calabi-Yau pair, XD, is a smooth projective variety X over C, and and a divisor D, anti-canonical divisor, which is reduced effective, has simple normal crossings. So, of course, you might probably want to consider things that are more general than this in terms of higher dimensional birational geometry. So things that have worse singularities like divisorial log terminal pairs or something. But for today, this is good enough, and this is a good thing to have in mind when you think about these things. So the interior of this thing, so the complement is called a log Calabi-Yau variety, which I'll just call LCY. And so these things behave a bit like, well, so let me firstly, let me just make a remark, which is that U has a holomorphic volume form up to scaling, which is just given by inverting the section that defines D. And so these things, so the kind of prototypical example of such a thing is the torus. So this is the kind of simplest thing to consider. And the pair XD that compactifies this thing will be like a smooth projective toric variety. And so, of course, in toric geometry, so what's the, okay, let me just for completeness tell you what the volume form in this case is. It's the standard torus invariant volume form, which usually makes more sense to normalize it by 1/2 pi I to the d, so that it has integral is equal to 1 over the torus, but it doesn't really matter because it's only defined up to a scalar anyway. And so associated to U are two lattices. So let's see, which way am I going? This is towards the door. Yeah. So U is C star tensor n for n some lattice, the co-character lattice, and the dual lattice traditionally called M. And so the points of N correspond to possible boundary divisors. In compactifications of U, toric compactifications of U, or the primitive vectors really maybe correspond to these, and non-primitive to multiples of them. And the points of M correspond to monomials. And there's a dual lattice, there's a dual torus which is, of course, C star tensor M. And if I pass to the dual torus, the roles of these two lattices are switched. And the reason that I introduce this is because it sets up nicely. So this kind of picture here generalizes in terms of, so this is an example of mirror symmetry between two log Calabi-Yau varieties, very simple, the simplest example. And so let me explain how this generalizes to more general pairs of log Calabi-Yau varieties. So I think this definition was given by Gross, Hacking, and Keel. So they define the integral tropical points a log Calabi-Yau variety U to be this space is called U trop Z. It's the set of all divisorial valuations on the coordinate ring of on the function field of U, which have a pole along according with for which this volume form has a pole. So and of course throw in the origin as well, because that doesn't belong to that set as so. And so if you do this thing if you write down what this set is for the torus, you'll find that it's the lattice N. And so this is a generalization. Yeah, it's divisorial valuations from CU star to Z, such that the valuation applied to the volume form is negative. It means that if I write, so if I pick a local generator, if I pick a local expression for this thing on the boundary, then it has a pole.
And that was that single valuation, a single divisor contact surface independent.
Yeah. So this is a generalization of n for C star to the D. And so let me then explain the conjecture that they made. Ooh. So here we go. So conjecture of Gross-Hecking and Keel. Is that, okay, so suppose that, so, okay, well, before I say that, so suppose U is, has a compactification XD, which is, so these are kind of technical conditions, but anyway, positive. So this means that D supports an ample divisor. And that implies, for instance, that U is affine. And maximal or maximally degenerate. So this says that D has a zero stratum. Then, yeah, has at least one, yeah. Then mirror symmetry is an involution on the set of such log Calabi-Yau varieties. So associated to U is a mirror, which is a variety of the same kind, such that so U has an additive basis such that let's say U star has an additive basis of the coordinate ring. So let's call this thing B. So these things are called theta functions. So this is called the theta basis. And these are parameterized by the integral tropical points of U. So and vice versa. So this is so this is like saying that not only is this space an analog of the character lattice for U, but it's also an analog of the co-character lattice for U. It's also an analog of the character lattice for B, and vice versa, right? And so the conjecture also says a lot more. So it tells you basically how to write down the multiplication rule between these theta functions, and that's I won't try and describe that, but it's defined in terms of counts of rational curves on U, or by passing to tropical geometry by counts of broken lines in something called a scattering diagram. And so let me, so this kind of generalizes the duality between dual tori in some sense. How much time? And so let me just, so Let me restrict to a subset of log Calabi-Yau varieties, which is very nice and easier to work with than in the general case, which is ones that are obtained from a Tauric model, which will be the case for the example that I discuss later on. So a Tauric model for a log Calabi-Yau variety U is a compactification XD, so to a log Calabi-Yau pair with a map pi XD to a toric pair such that this thing pi is a composition of blow-ups of so smooth disjoint hypersurfaces in boundary components. So the center that I'm blowing up actually has codimension 2 inside X, but it's a hypersurface inside a boundary divisor. And the reason that it's good to blow those up is because these are basically crepant blowups. So if I blow that, after I do all of these blowings up, the strict transform of this divisor B is the divisor D, and it's still anti-canonical, which is why I have this condition on. Yeah, I'll draw the picture now. Rational curves. Yes, yeah. Well, I'm allowed to blow, well, yeah, so strictly, yeah, in that case, yes. So I should say that that definition that I just gave is not the most kind of general. Of course, you want to consider arbitrary centers that are crepant for blowing up. So, I mean, if you were in the case where you're allowed singularities, then of course there's a lot more that you can do. And also you might want to blow the same thing up several times, which is also fine. But again, for the purposes of what I want to say today, that definition works. So for simplicity, I'm just assuming that we're in that situation. So the picture is, as Miles said, so here is my X, or let's say here is the T, and here's some boundary divisor, and it has some smooth center Z in it. And so because T is a toric variety, so let's see what color is actually going to be visible. Maybe yellow is okay. So I have this, let's say that I have this surface in here, which is isomorphic to Z times P1. I have this boundary, this Z down here is the thing that I'm going to blow up. And I blow it up and I get a picture like this. So so if I think about this kind of generically, like as a kind of P1 bundle over this boundary divisor, they're now reducible -1 curves in all of the fibers above Z. And so I can also blow down the strict transform of this yellow surface to get a different toric model. So now this is Z prime. And so this is called a mutation. So if I have a toric model, I can mutate it by doing these kind of elementary blow up, blow down procedures called mutations, and I get different toric models. And of course, it's obvious what happens to this center, but when I blow up and blow down, it might move all of the other centers around in the rest of the boundary divide. So that in general, there's more than one Z that I'm blowing up. There'll be some Zs in boundary divisors over here. And in order to work out what the toric model over here is, I have to work out what the transform of that, what the image of that bit over there looks like over here.
The thing you draw is the XD in the middle. I mean, two different reductions to toric.
Yeah, so this is a very simple case where XD is just the blow up of one thing.
Yeah.
But in general, it could be the blow up of many. But in this case, there's only two toric models and they're related by this mutation. Yeah. So the reason that the variety with the toric model is nice is because so we don't just want to do so I introduced the set of integral tropical points, but we also would like to have an analog of the real vector space in which those lattice n lives. So we kind of want an analog of NR to work with. And the way that we can do that is in this setting where a variety has a toric model is so we can construct a real affine manifold whose integral points are U trop Z. Well, it's not true that so it's not true that there's a real affine manifold whose integral points are the points that I introduced earlier. You have to allow the affine manifold to have singularities in the affine structure. So this is where this condition, real affine manifold with singularities, and so basically the affine structure of this real manifold can't be extended to the whole space at the same time. And so the way that you do this is, so take the fan of TV, the toric variety that is the base of the toric model, and throw away all of the cones of codimension at least 2. So basically, I'm only interested in the maximal dimensional cones and the walls in which they meet alongside, and then redefine the integral structure, the integral affine structure along each wall. I don't really want to write down explicitly how you do that, but the idea, of course, is that you have, so if I have two cones and they meet along some codimension 1 wall tau, then this corresponds to a curve C tau, a one stratum of D. And basically, for each pair, for every wall, I just map this cone into RD onto the appropriate fan of a toric curve with the same normal bundle as C tau. So basically, I just redefine where I see a wall, I just redefine that integral affine structure to make it look like what it would look like if it was toric. So this is now a manifold because basically the open patches are the interior of these two.
You're drawing a line in space on the left-hand picture.
Yeah.
That's not a dividing face between two cones.
This is the dividing face between two cones.
That's codimension 1.
Yeah.
But what did you say to her again? I can't follow.
So the top dimensional cones correspond to, well, so I mean, so when I do the toric blow up, basically because of all the centers that I'm blowing up are, I should have said that they intersect the boundary transversely, so they don't hit any of the corners, and basically they hit all of the boundary transversely. So topologically, so the boundary divisor D has exactly the same dual intersection complex as B. It's just that when I do these non-toric blow-ups, the curves that the centers intersect with, it will change their normal bundles when I blow those centers up.
Is this RD? I mean, I'm not following.
So this is just a map. So this is just, so define a map. So because everything is smooth here, because so I know that these two vertices, these cones are smooth.
Yeah.
So for instance, I send sigma 1 gets sent to the standard quadrant. So E1 up to ED. D is the dimension of the pair.
So this is a linear map.
This is a piecewise linear map, yeah.
The first cone identically, and the second cone will be.
Yes, yeah. So if this, yeah, okay. You happy? Or right. Anyway, there is a way. Basically, there is a way to you just define the affine structure on this thing according to what you think it should be, looking at the intersection numbers of this curve, the curve defined by this space with its the divisors that contain it. And so that defines, so this construction an integral affine manifold with singularities, which is, I guess, called U-trop. And shall I go all the way to here? Yeah. Okay, so let me just finish. This is the kind of end of the motivational kind of bit, but so there's a paper by Argus and Gross where they give a recipe to construct a scattering diagram in U trop when U has a toric model like the one that I've described, which is the data needed to define the coordinate ring of the mirror so given this is a bit of I'm using this as a black box, but given a log Calabi-Yau variety with a toric model, there's a way, algorithmic way to write down a scattering diagram. That's, I mean, it's a complicated process, and but it will give you a scattering diagram, consistent scattering diagram in this space that allows you to construct the coordinate ring of the mirror, and then you can set so then I have this, then I can construct V trop. So this will be an analog of M R, the character space. Sorry, over here it seems to reverberate the microphone a bit. So these two spaces have a dual intersection pairing which extends the one on integral points. So there's one on integral points, which is just given by I compute, so M correspond the points of U trop, let me call it N, correspond to boundary divisors in U, and the points of V by the conjecture correspond to monomials, these well, theta functions on U. So I can just evaluate the order of vanishing of a theta function, theta M, along the boundary component Dn. And this setup with these two real integral affine manifolds with singularities and this intersection pairing basically allow you to do a lot of things in this setting that you would do just with toric geometry. So there's a notion of convexity and therefore polytopes in these spaces. And so integral, obviously there are integral points, so you can talk about polytopes being integral, and so for example, and so on and so forth. So that's the kind of motivation which has taken up most of the talk. But so let me quickly mention so my talk title I talked about the three-dimensional Lineus map, and obviously a slightly more famous case is the two-dimensional Lineus map, which I'll just recall for you now, which you've probably seen before, even if it wasn't called the Lineus map. So it's the map that sends x1 and x2 to x2 and 1 plus x1 over x2. So, or equivalently, we can think about the recurrence relation xi plus 1, xi plus 2 is xi plus 1 plus 1. So if I iterate this, I get the recurrence relation, which I've just written down. And so very famously, this recurrence relation is 5 periodic and has a Laurent phenomenon, which means that if I expand all of the terms of this sequence in terms of any of the first two, so if I keep applying this map to this pair, I'll only ever see Laurent polynomials in x1 and x2 in these two entries. And so this is related to the Del-Pezzo surface of degree 5. And the Del-Pezzo surface of degree 5 is in turn related, is a section of the Grassmannian, so GR25. So let me just say that this is related to the Hooker equations of GR25. And so one nice way to represent the Plucker equations of GR25 is in terms of triangulations of a 5-gon. So if I label the Plucker coordinates on, so this picture I label all of the Plucker, every line in this picture has a variable attached to it, and it's convenient to label them as so. Y2, Y4, X2, X3, X1, X4, X5. And then the Plucker relations are given by flipping, if I pick a triangulation of this 5-gon, for example, this one. So this is going to have X5, X4, Y1, Y2, 3, Y5, Y2, Y4. And I flip one of these edges. So let's say I flip the edge X5. So like this, that gets flipped to X3. And the Plucker relation is then just the product of the two edges in the diagonal of this quadrilateral. So there's a quadrilateral here, which is gets flipped. So the product of the two things in the middle is the sum of the product on the two things on either opposite edge. So this is X4, Y4 plus Y1, Y2. Anyway, I just wanted to describe this because give a similar kind of, how much time have I got? 20 minutes. Description of the three-dimensional Lineus map in a minute. So the point so if I look at I have a division of the 10 Klucker variables on GR25 into two sets of 5 here. And if I look at the vibration that I get, so if I let U be the affine cone over GR25, then if I look at the vibration that I get by over setting all of the over the affine plane defined by all of the y variables, say the guys that are up here on the outside, then this family here is a flat family. Yeah, of affine Delpezzo surfaces. Of degree 5, which degenerate over the origin to cone over a pentagon. So each fiber is a dp5 minus an anti-canonical pentagon of -1 curves. And so in particular, each fiber has a compactification as a dp5 with an anti-canonical pentagon of -1 curves. And so Tauric model for this thing U, which is going to be a fiber of this map, just a general fiber for U is so there's a toric surface whose fan is given by this picture. And in order to get the Delpezzo surface, I have to blow up one point here and one point here. And what that corresponds to doing is changing. So the two edges here, where the self-intersection was 0, I now have to bend the affine structure along these edges, which means that any line that comes in, pass through one of these lines, bends as it travels through, according to a formula that you just have to work out in order to get the picture right. Yeah, so
What is that then?
So I started with this. This pentagon is the toric surface defined by this fan. And if I blow up 2 points on it, so it's a toric Delpezzo of degree 7. So if I
as I'm moving around this A5 base state,
Yeah.
why are we just saying small?
So basically, in the base space of that thing, all of the fibers that live in this dense open torus are isomorphic. They're isomorphic to that thing. And as I hit if one of the yi's ever becomes 0, then there's some degeneration happening.
Yeah, so you're saying that's described by what you blowing up? You're blowing up 2 points.
On each of these two curves of self-intersection 0. And then that's the del Pezzo of degree 5 with the anti-canonical pentagon. So this is the fan for the toric variety, and in order to make it into the integral affine manifold that I was talking about before, I have to do this thing where because I've blown up these 2 points on these 2 edges, I have to redefine the affine structure along these 2 lines by allowing lines to bend as they pass through them. And so this is, so obviously these correspond to boundary divisors. The lattice points on these rays correspond to these 5 boundary divisors. But if you've seen the scattering diagram for this cluster algebra, then this is exactly the same picture. And these, so this is the space U trop. And as it happens in this example, this is isomorphic to the space V trop, and there's a 1-to-1 correspondence between the boundary divisors, the di's, and the cluster variables, the xi's, so this surface U is self-mirror, and there's a naturally duality here between the xi's and the di's. And there's the intersection pairing between these 2 spaces is given by evaluating the order of vanishing of the xi's along the di's and vice versa. So yeah, the polytope given by this pentagon here, it corresponds to this kind of compactification of the toric variety. But you can play around with this and have there are other ways to other things you can do here. So for example, if I were to blow up one of these points, to get a compactification like this, it would correspond to a polytope that looks like this, and so on. So there's different ways to think about compactifications of this surface in terms of polytopes in this space. And I was going to give more examples, but I really want to say something about the 3-dimensional case. So let me just move on and say something about that briefly. I need to move the camera. So the 3-dimensional Lyness map. So this is a kind of example 1 dimension up, which is a kind of like a big brother to the del Pezzo surface that I just talked about. So the 3-dimensional Lyness recurrence relation is the thing that you get by extending the recurrence by length 1. And this is fun because it's 8-periodic. And it has a Laurent phenomenon. But this thing fails for dimension bigger than or equal to 4. So once if I were to extend this thing one more time to get a 4-dimensional recurrence or a 5-dimensional recurrence, then it's no longer periodic and it no longer has this nice Laurent phenomenon. But at least in this dimension 3 case, it does. And one way to understand it is that there's also a homogeneous variety lurking in the background here. So it's related to the homogeneous variety OGR 510, but actually I prefer to think about it as OGR 49. So OGR 49 is isomorphic. So OGR 510 is has 2 components, and each component is isomorphic to OGR 49. So this is an orthogonal Grassmannian. Let me just explain a kind of similar combinatorial game you can play to get the equations of the orthogonal Grassmannian. So it's a homogeneous variety for the spin representation of SO9. And the thing you need to know about this is that the weight polytope of this spin representation is a 4-dimensional hypercube. And so it has 16 vertices, and if I project them onto the Coxeter plane, I get this nice picture of projection of a hypercube. So let's it's ambitious to think that I could draw this there we go. That's so this is a 4-dimensional cube that's been projected into a 2-dimensional plane, and it has a 8-fold symmetry, which is the order of the Coxeter element for B4, which is the associated, which is the type of that that group. And so there are 8. Of course, the 4-dimensional hypercube has 8 faces, and the faces are 3 cubes, and so you see some 3 cubes in this picture. For instance, like here, so this is a 3-cube face, and these 3 cubes can be used. So so the equations for U, so for OGR 49 come from what's called the cube recurrence, which is that if I see a cube like this and I label all of the variables on the vertices like this, say, then I write down the equation AB is CF plus DG plus EH. So similar to the thing that we had before. And so if I label if I just go back to this picture for a minute, if I label, oh, yeah. Okay. If I label all of the guys in the middle, x1, x2, x3, x4, and I label all of the things on the outside as 1, then actually I think I don't want to label them like this. I think I want to label them x1, x4. I want to go up in 3, so x7, x2, x5, x8, x3, and x6. So the reason for that shift in 3 is just so that when I compute the equations according to the cube recurrence that I had before, then I get the equations for the Lineus recurrence. So if I do this big square on the top here, this cube on the top here, sorry, this red cube, the two guys in the middle are x1, x4, so I'll get x1, x4, and I've got x2 times 1, x3 times 1, and 1 times 1. So I get the cube, I get the Lineus recurrence from this picture, and the 8 periodicity is just the rotation of this cube 8 times, of this picture 8 times. So similarly to the previous case, okay. Similarly to the previous case, we can consider a fibration. So let's say that U is the cone over OGR 9, and let me project to the 8-dimensional space of yi's, where the yi's are going to be the variables on the outside. Then the fibers of this thing are affine Fano 3-folds of type V12, and if I take the general, so they degenerate to the cone over this polytope here. So it has 8 P2 components and 2 P1 cross P1 components. And I can describe to you a Tauric model for each fiber. So if I let U be a general fiber of this vibration, then I can, so it's a 3-fold, affine 3-fold in this space here, and I can just consider the projection to A3, given by x1, x2, x3. And if you look at what happens in this map, so it's an isomorphism over the dense torus, so it's basically from the Laurent phenomenon, and over the boundary divisor, so over the 3 coordinate hyperplanes of A3, we get 3 divisors in U are contracted to, so they're contracted to a line, and a conic. So it's very actually interesting that these lines and these conics, this conic meet in the boundary like this. So so this is like, this is x1 equals 0, and this is a line of the form ax2 plus bx3 plus c is 0. And this is x3 equals 0, and that's a line, similar equation. And this conic is in the plane x2 equals 0, and it's of the form x1, x3 plus d x1 plus e x3 plus f equals 0, something like that. And so basically, if I blow these three lines up, then I get a toric model for this cluster variety U. So I can write down. So I have a toric model for it, and I can write down these tropical space.
You've got three surfaces there.
Yeah, so these are the three coordinate hyperplanes in A3. And so basically the image of U in this space is this constructible set, which is given by the torus union with these three lines, these three curves. And if you work out what happens, so if you want to understand what U was, if you blow these three, so there are three divisors in U, which are like ruled over each of these. So I'm basically just blowing up these three lines to resolve this map. So that gives me a toric model, and then I can write down a scattering diagram. And then if you run the, so how badly over time am I? I'll just summarize in 2 minutes the rest of what I wanted to say. Apologies for being late. I was overambitious. So if I mutate either line, so if I mutate this line is of the form something like this. So the mutation is given by sending x1 to x1 prime, x4, say, which is a x2 plus b x3 plus c over x1. So this is basically the kind of parameterized version of the Lineus map. So those two, mutating either of these two lines is basically the order 8 automorphism that was coming from the Lineus map. But then there's one other center here, which is this conic. And if I blow up this conic, I get a different toric model. So the conic gives two new cluster variables. So Q1, which is going to be the equation of the conic divided by x2, and Q2, which is actually the image of this Q1 under the Lineus map. So it turns out that Q1 is an invariant for the square of the Lineus map, which is a surprise. And so I guess the proposition is that x1, x8, q1, and q2 form a closed system of cluster variables related by mutation. So there's an exchange graph which I'll draw for you. So this is something like a finite type cluster algebra, except that it's not strictly speaking a cluster algebra, because there's no skew symmetric matrix or quiver involved. And so this is the exchange graph. So every vertex in this picture denotes a torus. And if I label the edges like the faces like this, so the face, the pentagon on the back here is x2, the pentagon on the back here is x4, then and then this face is q1, then the initial torus that we started with was the one with coordinates x1, x2, x3, so that's that vertex. And this was the Lyness map, which corresponds to blowing up these two lines. And if I blow up the conic, that corresponds to traveling out in these directions from each of these 8 possible seeds. And the only thing that you need to check is that actually this all closes up very nicely. And the nice thing about this is that this is 10 variables. And these 10 variables correspond to these 10 boundary components. The picture is exactly the same, except that I've contracted these blue edges here. And the same fan that describes the toric model for this threefold also describes the scattering diagram for these 10 cluster variables. And so the tropicalizations are, this space U-trop is both the scattering diagram for the mirror and the toric model for U. So this thing is self-mirror. And it's just like the dimension 2 case before it, there's a nice duality between this space. And so you can start playing kind of toric geometry style games with this variety, the variety that's the general fiber of this thing. So it's basically behaves a lot like a toric variety. Once you set this machinery all up, you have a space which has a lattice inside it, or integral points inside it that parameterize both functions on that space and divisors on that space. And yeah, anyway, I've gone way over time, so sorry about that, but I'm finished. You can all breathe.
Okay, I will stop the recording. Are there any questions?
Yes, I have a question. So